best we can. I still think you guys are getting a better deal than the people who are like all online, right? Like, goodness gracious, all online is such, whew, as a student, it's got to get awful boring after a while, right? So let's talk about systems of equations. And two variables, and for the most part, we'll take those two variables to be x and y, typically. But you could switch those out for something else, right? So how do we solve? That's really the question is how to solve two linear equations at the same time. So sometimes people, instead of saying at the same time, they'll use this kind of more fancy word. They'll say it's simultaneously. Right? All right, so, is it possible? What happens? What does the solution look like? So let me just start with an example. Suppose we're given 3x plus 2y equals to 6, and we're given that x minus y is equal to 1. Right? This would be two equations in two unknowns. How can we solve a system of two equations and two unknowns? Right? I will add a second bullet point up here. How to solve two linear equations at the same time. My second bullet point I would add is, what does the solution look like? Or I might add a third bullet point. How can we visualize the solution, right? These are things we want to talk about. Okay, so you guys, can you give me any advice? How should we solve this? Okay, so like isolate one of the variables, which maybe the second equation would be good, right? So, I'm going to number this equation 1 and equation 2, and I'm going to say solve equation 2 for x equals to 1 plus y, right? And then what do you want to do next? I'll put you in the driver's seat. Multiply everything by 3. Oh, so you're saying, but you're thinking about doing that up here, right? No? But you already made me solve equation. But you already made me solve equation 2 for x. I mean, I like what you're saying. We're going to do it that way next. But it's good. It's very good what you said. That's the better way to do it. But since we went down this path, I was fishing for you to tell me to put, substitute into, let's call this thing 3. Substitute 3 into 1. So if we substitute 3 into 1, we'll get 3 times 1 plus y plus 2y equals to 6, right? And at that point, we're in the home stretch, right? Because we've eliminated one of the variables, and we just have what? One equation, one unknown, which you guys are going to obliterate on the test next Monday, right? I hope so. I hope so too. So this is a very potential test 1 question. So good news, we get to review for test 1 even in this lecture. So let's see here. We distribute, right? This gives us 3 plus 3y plus, yeah, I heard a 5y, I'll agree. So this gives us 5y equals to 6 minus 3. So y is equal to 3 divided by 5. Are we done? So I subtracted 3 to the other side, and I added these two together, right? So like it's like minus 3 over there. Right. Oh, so in the second equation, what else could I be lazier with something I already have on tap, so to speak? I could use 3, right? But I agree with you. Alternatively, you're right. You could plug y into any of the 3 equations we have. If you plug it in, you'll just have x left over, and you can solve for x. I'm going to use 3, though, because that gives me x is equal to 1 plus 3/5, which is 8/5, right? So we get x equals to 8/5, and y equals to 3/5. So oftentimes, because we're solving them together, we write the solution as a pair. So the solution, aka 8/5, comma 3/5, solves star. And you're like, well, what's star? Well, I'm calling this system, both of these collectively, I'm calling them star. Okay, like star is the name of the system of equations. We have to solve both equations at once. Did I ever hit record?
I think so. You walked over here? Yeah, it's working.
Okay. It is disconcerting. Okay, so the way we just did is called elimination. So the way elimination works is you solve for one of the variables, and then you take that and you plug it into the other equation, and that's how you go. Elimination you can always use to solve these problems. This is a way to do it. The other way to do it is what you were talking about, which is to make the equations look the same, and then use adding equations or subtracting equations. And that's usually faster if you can see it. So like this one, you were telling me take equation 2 and multiply by 3, right? So that would give us, I'm going to do it over here. So basically 3 times equation 2 would give me 3x minus 3y equals to 3, right? And then I also have equation 1, still the same, 3x plus 2y equals to 6. So one of the things we can do with 2 equations is we can either like subtract equations or we can add equations. And what I mean is you subtract and add both sides the same, like left-hand side minus left-hand side, right-hand side minus right-hand side. So like in this case, think about it like this. When we subtract the equation, the 3x's cancel, and on the other side we get minus 3y minus 2y equals to 3 minus 6, which gives us what? Minus 5y equals to minus 3. So what does y equal to? Minus 3 over minus 5, 3/5. Great. So yeah, so this one, 3 times 2 is 3 times x minus y. That is a good question. Please ask these questions. 3 times 1. So when I distribute the 3, I get 3x minus 3y equals to 3. 3 times equation 2. Like when we multiply equation 2 by 3, it has to distribute to both the x and the y term. Is that what you're asking about? Or is it a different 3? Where's the 3 coming from? Yeah, I mean, it's because there was a 1 and a minus 1 and a 1 here, and when we multiply those by 3, it all becomes all 3's. Now, once you have 3/5, you can just do like we did over there and plug it into the other equation. Right? So like plug into 2. I'll use 2 this time. That would give us x minus 3/5 equals to 1, which would tell me x is equal to 1 plus 3/5, which is, by the way, 8/5. So as you can see, we get the same answer, right? So these are, let me just point out, let me say it in words here. Method. One method is called elimination. Basically, isolate a variable. You isolate either x or y, then plug into remaining equation not yet used. So like, it's important in this one, in our first method, we found that x was equal to 1 plus y, right? If we had plugged x equals to 1 plus y into equation 2 again, we would have gone nowhere. What happens if you plug x equals to 1 plus y into equation 2? You get 1 plus y minus y equals to 1. You get 1 equals to 1, which is true, but useless, right? It was important in our first method that we plugged equation 3 into equation 1 because equation 1 is the one we had not yet used. So if you do some steps and you come back to like 0 equals 0 or 1 equals 1, you probably plugged it into the wrong equation. We do need to like meaningfully use both equations to solve it. So that's elimination. The other method is addition or subtraction, and let's say scaling of equations towards elimination. So the goal is always elimination. Like the goal is always to get rid of one of your variables and just have one left over. It's just the addition and subtraction of equations is another way. There's a third way to solve, which is graphical. The graphical method of solution is by far the least practical, right? Like, what would the graphical method look like in this? We'd have to plot these two lines, right? So like, the one is easy enough, right? Equation 2 is what? Solve for y, what do you got? I heard it x minus 1. I'll buy that. So we have slope 1 and a y-intercept of minus 1, right? That might be a question on the test next Monday, right? Here's an equation of a line. What's the slope? What's the y-intercept? That is totally on message for the test Monday, isn't it? So, you know, or the quiz Wednesday, I suppose. But there it is. This is y equals to x minus 1. How about the other one, equation 1? What's that? If we solve that for y, what do we got? What's this one here? Solve that for y. We've got 2y. Right, so, sorry, I'm kind of running out of board space here. Y is equal to 6 minus 3x over 2, which is 6 over 2 minus 3 halves x, which is 3 minus 3 halves x. So the y-intercept is 3, and the slope is minus 3 halves, right? That's kind of sort of something like, I don't know, roughly speaking. And if you had graph paper and you did this super careful, you could look for the point where both of those lines intersect, right? Because each one of those lines is the collection of all points like x comma y that solve that equation for the line, right? And so if you think about where they intersect, that's where both equations hold true for that point of intersection. So graphically, the point of intersection corresponds to the solution. In fact, without doing even so much as another bit of graphing, I can tell you the point where these two lines meet is the point 8/5, comma 3/5, which is kind of neat, right? So that's the graphical meaning for the solution as well. Now, I do not advocate for the graphical method of solution, right? Because you guys want to carry graph paper around and a ruler and like, it would be very laborsome, right? I mean, it would be very labor intensive to do the graphical method. So we're mostly going to aim for elimination or the adding and subtracting trick. Like that's the way we do it. Okay? Let's work a bunch more examples. That's the way to understand here. Solve x plus y equals to 2 and x minus y equals to 0. So what do you guys advocate we do here? I'll number those equations 1 and 2 so we can talk about them.
Can we combine the two x's and add it by the two y's,
Mm-hmm.
making it equal 2 plus 0?
I think that's a good idea. Add equations, you say? So we have x plus y equals to 2 and x minus y equals to 0. You want to add these? Like just add the equations? So when we do that, you say we get 2 x's, right? And the y's cancel, right? Y plus minus y, 0 y's, and 2. Therefore, x equals to 1. And now how do we find y? Yeah, I mean, it doesn't matter. Like, you can either use equation 1 or equation 2. Which one do you want to use? Equation 1? Okay. We get 1 plus y equals to 2. So that tells me y is equal to 2 minus 1. So y equals to 1. So the solution is 1 comma 1 in this case. Is good? All right. Let's take a second here to sort of smell the roses. What does this mean graphically speaking? Does this make sense graphically? Just, right. Graphical appreciation. Remark. So this is not part of the solution, right? I just want to stop and say, what does this mean graphically? Like 1 is what? 1 is y equals to what? 2 minus x, right? And 2 is what? Well, that's y equals to x, right? So we've got a line through the origin with slope 1. And we've got a line through y-intercept 2, right? Y-intercept of 2, slope minus 1. these are in fact perpendicular lines, aren't they? Because they have reciprocal negative slopes, right? Like 1 is equal to 1 over minus 1 is equal to 1 over minus 1. Yes. These are perpendicular. And the point of intersection is right here, right? 1, 1. Yep.
Wouldn't that be intersecting lines?
They are intersecting lines, right? But they're perpendicular. Did I say parallel? No, I don't think so. What is it? I mean, are you asking if are they intersecting?
No, I thought it was supposed to be like intersecting.
I mean, I totally agree. These are intersecting lines. Usually lines are intersecting, right? What's the one case where it doesn't happen? Let's look at an example. We gotta watch out for this one. You might wonder, like we've done 2 examples now, and so there's a question: does it always work out like this? Like when we try to do these things, do they always work out like this, right? So one thing I could have like x equals to y, and I could have 2x minus 2y equals to 0. All right, this is still a system of linear equations, but it's not written in what's called standard form. Okay, anyway, how would you solve this, or try to solve it? Oh, and I'm sorry, I didn't mean to put a 0 here. I meant to put a 2. There. Now I feel better. I think this one kind of says try elimination, right? So if we take equation 1, plug in 1 into 2, what does that give us? 2x minus 2 times what? 2 times x, right? Equals to 2. What's 2x minus 2x? 0, all right. And so we just find that 0 is equal to 2, which is not true, right? So that means that this given system of equations is not consistent. There is no solution. So not all lines intersect. Because when lines do intersect, we do have a solution. I totally agree with that. And they don't have to be perpendicular to intersect, right? Like that previous example over there, those lines aren't perpendicular, right? The one on the red one in example 2, rather the red one in example 1 had slope 1. The blue one in example 1 had slope minus 3/2. Those are not perpendicular, right? They're just what's called skew. This here, if you just take equation 2 and solve for y, what do you get? You get x plus 1. Whereas the first one, of course, you just get y equals to x. So if we plot both of those on a plot, right, to graph both of those at once, what happens? We got the line with slope 1 through the origin, right? We got the line with slope 1 with y-intercept of 1, right? What's the point of intersection for those? See, there is none, right? So in the context that we have 2 equations and 2 unknowns, and those 2 equations correspond to lines which are parallel with this, meaning they have the same slope, if they have different y-intercepts, there's no solution at all.
So we don't have a substitution for either of the variables?
If I would say it this way, if after you do the substitution, you come to an equation like 0 equals 1, or in this case 0 equals 2, that shows that the original system is inconsistent. Because you've made logically, you've changed your equation in like logically equivalent ways. See, the thing is when we add the equations or when we multiply the equation by a non-zero number, it does not change the solution set. So if we engage, and same with like the substitution, if we do substitution, it will not change the solution set. So as long as we limit ourselves to these allowed operations, if they bring us to a new system of equations, which is inconsistent, then we can logically deduce that the original system doesn't have solutions. And so, but graphically, the other way to see it would be graphically. Graphically, there's no solutions if you got like parallel lines that have different y-intercepts. So we've seen already there can be a unique solution, there could be no solutions at all, right? So this is no solution was the answer here. No solutions. And let's look at example 4. I'll give us another example that's kind of in a nice format. So let's do like 3x minus 2y equals to 0, and 6x minus 4y equals to 0, right? So if we try to solve the system of equations, I mean, and we can, I'll tell you right now we can, what happens? When does this class start? 125 or 125? Okay, I was thinking 145 all of a sudden, but that seemed wrong. So that means, so we end at 3?
240.
240, okay. You're like, it wasn't funny the first time, it wasn't funny the second time, it's still not funny now. Stop already. All right, fine. So what do you guys think about this one? What I would say about this one is if we take equation 1, right, and we multiply it by 3, what happens? So 3 times 3x minus 2y is 3 times 0, right? Which is giving me what? Did I say 3? I meant 2. I'm a moron. 2. 2 times equation 1. Good grief. 2 times equation 1. So 2 times 3x minus 2y gives me 6x minus 4y equals to 0. But what is this? This is just equation 2, right? When this happens, when one of the equations is just a multiple of the other equation, right? If you can rewrite one equation to just be a multiple of the other equation, then these are said to be dependent equations. Yeah. You want to ask me a question? Dependent.
What does that make the answer?
Aha, that's a good question. What is the answer in this case then? So the answer in this case is solve for whichever variable you like. I'm going to solve for y. So y, so I've got 3x equals to 2y. Y is equal to 3/2 x. And solution set is x, comma, 3/2 x, such that x is a real number. Or you could write it as a sentence. You could say that the solution is y equals 3/2 x for any x. You're like, doesn't seem like you really did anything there, does it? I know. Let me explain to you why this makes sense. So, what are these equations? Like, what happens when you look at these graphically? Equation 1 is what? Y equals 3/2 x, right? What's equation 2? When you solve for y, again, y is 3/2 x. So these two equations, if we think of them graphically, they're the same line, right? But the solution is where the two lines in question intersect. Where does a line intersect itself? Everywhere, right? So the solution is all points on the line, all points. And in this rather special and somewhat silly case, we get infinitely many solutions. So if we have parallel lines which have the same y-intercept, in that case, the solution set is infinite. So basically, any point on y equals 3/2 x solves the given system. So, like, could you give me like 3 different solutions on this for this equation? I'll get us started. 0, 0 is an example of a solution.
1 and 1.
So, like 0, 0 is in here. I heard a 1. What if x is 1, what's y?
3, 2.
Yeah, 3/2. If we put in x equals to 2, you get y equals to 3. I mean, my point is to you, you can start listing as many points as you like, and you can just keep listing them and listing them and listing them. These are all, when you plug those in to the equation, they work, right? Let me show you what I mean by that. What do I mean when I say that 2, 3 is a solution to the system of equations? What does that mean?
You depend on the line.
Right? My claim is 2, 3 solves 3x minus 2y equals to 0, and 6x minus 4y equals to 0. How do you... Oh, you got it. Okay. How do you make good on that claim? So that means we're going to set x equals to 2 and y equals to 3 and plug it in. So 3 times 2 minus 2 times 3 is equal to 0. Check. Right? And 6 times 2 minus 4 times 3 is also equal to 0. Check. So that shows that the point 2, 3 solves that system of equations. So, you know, you guys do not have to write the solution with this fancy schmancy writing over here that I did, right? I mean, I'm totally fine with you guys just saying that the solution is y equals to 3/2 x for any x. Like, that works for me just fine for that case, all right? But that's it. So when we have 2 equations and 2 unknowns, there's either a unique solution, right? There's no solution at all, or there's infinitely many. Them's your choices, as long as we're looking at 2 real equations and 2 variables. And that geometrically corresponds to the fact that that you have 2 lines. They're either skew, so they intersect somewhere. They're parallel, and they have different y-intercepts. They intersect nowhere. Or they're just the same line, in which case every point on the line intersects itself. So let us do another. So I'll try to spend the rest of the class. I'm not going to do any more graphing. All right, I've said what I have to say about graphing here. I'm just going to focus in on just the technique of solving the equations for the remainder of class. All right. This is example 5, is it? All right. All right, 2x equals to 3 plus 8y, and x minus 3y equals to 2. So sometimes the problem comes to us in a format which is kind of annoying, right? So like the first thing I do when I have something like this is like reorder things. So all my x's and y's are on one side and my constants are on the other. That's just how I function. Your book seems like it is promoting putting everything equal to 0. You could do that. It is not how I have classically solved these problems, and I'm not convinced it's wise. 2x minus 8y equals to what? 3, right? And x minus 3y equals to 2. Right? I propose that we label these equations so I can talk about them systematically. I'm going to call this equation 1. I'm going to call this equation 2. And so let's see here. Any ideas? Minus 8y equals to 3 minus 2x. That's from 1, right? So that tells me that y is equal to 3 minus 2x over minus 8, right? So what you're going with is elimination. So you can, all right. So we're going to take this and we're going to plug this into what? Plug into 2. That's right, because we just used 1. You got it. And so 2 gives me x minus 3 times that mess. Equals to 2, right? Oh, yeah. Now, we're almost done. We're in the home stretch, right? Because now we have one equation and one unknown, which we already know from studying for quiz 1. We're bored with this problem at this point. We were ready to destroy this problem in the quiz today. That didn't happen. So, you guys are like, it's like taking candy from the proverbial baby. Which, as I always say, is a bad saying, because if you've ever tried taking candy from a baby, it's actually quite difficult. Especially ring pops. If they got a ring pop, they're not going to let that go. I'll say that right now. What would you do? You know what I would do to this? I would multiply this thing by 8. Because I don't like that fraction. So we can get rid of the fraction by multiplying the equation by 8, right? So I'm going to do that. Multiply by 8. Or we could multiply by minus 8. I mean, what do you guys want? 8 or minus 8? 8, okay. So 8 times x minus 3 times 3 minus 2x over minus 8 equals to 8 times 2. Distribute 8x minus 3 times 8 times 3 minus 2x over minus 8 equals to 16. I'm going to cancel those 8s now. Notice that I have a net of a minus times a minus, which gives me a plus, right? So I get a 8x plus 3 times 3 minus 2x equal to 16. We're getting onto the part of the board where my writing is illegible, so I'm going to come back up here. So what I've got is I've got 8x plus 9 minus 6x equals 16. And that gives me what? That gives me 2x is equal to 16 minus 9, which is otherwise known as 7. So x equals 2? 7 over 2. And then I would suggest we go back to the Pac-Man. And feed Pac-Man. Feed Pac-Man. X equals to 7 over 2. Num, num, num. And when you do that, you get y is equal to 3 minus 2 times 7 over 2 over minus 8, which is to say that y is equal to, the 2's cancel. 3 minus 7 is what? Minus 4. So we have minus 4 over minus 8. Yeah? Also known as a half, right? So therefore, my solution is 7 halves, comma 1 half.
Why did we multiply by 8 way back then?
Because we hate fractions. They're like
Where does that 8 come from?
they're like Thanos. We want to destroy them. What's up?
Where did the 8 come from? Like when it says multiply by 8, where are you getting that from?
I mean, I just thought of it. I mean, it was just it was a creative leap. It was because I have eighth up here, so if I want to get rid of it and not work with a bunch of eighths, just cancel multiply by 8. Yeah.
Why didn't you multiply, where the 3 is, right under where you put multiple by 8, the 3, why didn't you multiply 8 times 3 right there? Because you distributed 8 in x, and then you didn't distribute it to 3.
Here?
No, over.
At the bottom.
Yeah, what you did.
This here?
First one. When you were multiplying, you did 8x, then why didn't you do it to the 3?
Well, but I did. I put the 8 right here. I mean, 8x is this, right? That 8 went there, and then it also goes over to here to give me that one. This 8 was not here before. That's from distributing. But then it went away because the 8 cancels with the 8. I hope you guys won't be upset with me when I tell you that this is not the way to solve this one. Uh-oh. I broke her. This is, what I'm trying to say is, you know, when you understand elimination, it's kind of like a hammer, you know, everything looks like a nail. You can do it, right? But is it the right thing to do? I'm not convinced it's the right thing to do. Like, personally, when I'm solving systems, if I can see a way to subtract or add the equations, it's usually nicer. And I think that's the case here. So same example, but let's use the other technique, the adding, subtracting equations technique. So I've got 2x minus 8y equals to 3. And I've got x minus 3y equals to 2. What can you do to make these equations like line up? you're totally within rights to do what we did, And I'm glad you did, because it illustrates the point. This will illustrate the point of why we should try to do it the other way. And I'm not saying that it's universally the case not to use elimination. That's not at all what I'm saying. It's just that some problems it works out better to do it this way. I think this one, I mean, I don't know. If there's enough fractions in the problem, it's just ugly any which way you do it. That's just all there is to it, So I'm multiplying by 2, all right? So we get 2x, and then 2 times 3 is 6, so I got the minus 6y. Do I need to write that out? Multiply the second equation by 2. And the reason I did that is to make the 2x's, my goal here was eliminate the x's, right? So goal, get the 2x to cancel.
So when we have an equation like that, in order for us to get rid of the x or the y, we have to find a number to multiply to make it equal the first or second equation.
Right, you need to do something, multiply by some number to make the things match up. It's possible that you have to multiply both equations by some number to make it match up. Like there are problems like that. We'll work one like that next.
So we are subtracting that.
Yeah, let's subtract, because then the 2x's cancel, and we've got what? Minus 8y minus a minus 6y equals to 3 minus 4, right? Which gives us minus 2y equals to minus 1, so y is 1/2. And somehow that fraction of 8, it never manifested itself in this solution, did it? Which is funny, right? And then how do you find x?
Plug it in.
Right, I think I would try to be as lazy as you can, right? Once you find one of the variables, go back and look at your list of original equations, ask yourself, which one is easiest to plug, to work with? To me, this one, right? That one says x is equal to 2 plus 3y, right? But y is 1/2, right? I added 3y to the other side. So I solved this for x. Very, very good question. / comment. I'll allow both. So what's 2 plus 3/2? I mean, that's what, 4 halves, right? 4 halves plus 3 halves, 7 halves, right? So, of course, again, we find that same solution. Now, part of the reason that the second solution was easier is just because we've already got this problem in our brain. We've solved it the first way. That just makes the second solution seem easier than it actually is also. That's like, so here's the other thing, is like the adding and subtracting equations, it does involve a certain cleverness. And so if you don't have that inspiration on how to make the things match up, then maybe you have to fall back on elimination. But elimination comes at the cost of working with fractions carefully. You have to work with fractions carefully in elimination, because it's just going to happen. Let me look at another example with you guys. Again, I'm going to put you guys to work after this. After the test, we come back, you will have a list of problems. You're going to work them yourselves, and then we're going to talk about their solutions. So that's the way that's what we're going to next in here. Example. I think that'll work better. Here's one. 3x plus 4y equals to 7, and 5x minus 6y is equal to minus 1. So this one's annoying in that you can't just match up the numbers, right? And elimination is also a bear here, right? I mean, because like anything you solve for, you got fractions out, coming out of your ears. So I think the way to do something like this is you look for like the least common multiple of like a pair of coefficients. I suggest we look at the 3 and the 5, right? So if I do, say, 5 times 1, and if I do 3 times 2, then that will give me 15x plus, let me write out the steps, otherwise I'm going to lose you guys. All right, so 5, come on, 5 times 3x plus 4y equals 5 times 7, and 3 times 5x minus 6y is equal to 3 times minus 1. So then we'll clean those up. Clean that up, what do we get? We get 15x plus 20y equals to 35. And 15x, 3 times 6 is 18, right? So minus 18y equals to minus 3. See, this was my plan, was to make the x terms match up. And I knew if I could, find them a common ground to meet on, which was 15, then I could do it, right? Multiply the first one by 5, multiply the second one by 3, meet in the middle at least common multiple of 15. Yeah, I think then you want to do what? You want to subtract, right? But yeah, then you got to add or subtract and kind of see where you go. All right, so subtract. We've got what? 20y minus a minus 18. Y is 35 minus a minus 3. Be careful with like keeping account of the minus a minus, right? Easy place to make a mistake. So I think that gives us 38y equals to, 38. So what's y equal to? Y equals to 1. Are we done? We're not done yet, right? We still need to figure out what x is. Plug it in? Yeah. And so, like, it doesn't matter. They're all equally ugly. Pick whichever one you want. I'll use equation 1. I'll say use 1 with y equals to 1. We get 3x plus 4 equals to 7. So 3x is equal to 3. So x is equal to? X is equal to 1. So the solution is 1, 1. How do we check our solution? That's a question I should ask you guys. How do we check our solution? Checking your solution is something you should always do because it doesn't take much time to make sure that you did it right, right? It's so easy to get twisted just a little bit and make a sign error or something. And you can find out whether or not you did it right or wrong here by going back to the start and plugging it in. Just takes a minute, and you can... Yeah, right. So let's see here. 1, 1. So we're going to do 3. Let's see here. 3 times 1 plus 4 times 1 equals to 7. Yay. And 5 times 1 minus 6 times 1 equals to minus 1. Now, to make this check, actually worthwhile, you need to actually do what? You can't just like write the number down and write the check and just say, check's in the mail or whatever. You need to actually think through that and actually make sure that the numbers work out like we claim there are, Make sense? Example 7, and this will be it for today. So 17x minus 3y equals to 2. And 2x plus 4y equals to 8. All right, now for the audience participation. Give me a number, any number.
Let's do, I
I heard he beat you to it, 2. What was, you come up with a number now? 2 what? I can't put, it's not a number. 6, all right, I'll take 6. Is 2 comma 6 a solution? 2 star. Now, if it is, it is. If this is a solution, I will buy pizza for the class, next class.
So if this is a solution, we all pass the first test. Like the quiz. No, test. Test is much more.
I probably just made a promise I can't keep. And I have not. I will admit I have not read every line of the COVID policy, but I'm guessing bringing pizza to class is forbidden right now.
Okay, since the quiz is left, I'll give it to you. We all pass the quiz.
Let's not get so excited here. I'm pretty sure that it's not. So 17. It's kind of academic. Why have we agreed that saying something's academic is like some kind of derogatory phrase? And why is that allowed in America? Like it's just academic. It's not. It's anyway. So 17 times 2 minus 3 times 6. What's that equal to? I mean, it's 34 minus 18, which is what? 2. It's 2. That is funny. Who said that? Yeah, you're wise. But it isn't correct. 24 minus 8. 60. Is it 16? Is that 16? I think it's 16, right? Which, of course, is not equal to 2. And so game over. If your point fails to solve even one of the equations, that's all it takes for it to be not a solution. To be a solution to a system, it has to solve both at once. So, sorry, I made another reference to Thanos, I know. Oh, have you watched it? Since our last conversation, have you've still not partaken in the Marvel Cinematic Universe? But I heard that Fast and Furious 9 might be in space. I read saw something about Fast and Furious in space, yeah. I don't know how that works exactly, but do you know about that? It's because, like I said in our previous conversation, Vin Diesel's actually an Asgardian, so he just gets on the Bifrost and he's going wherever he's going and takes his friends with him. See, but I can't say more about this because you do not know about the Bifrost, as you have not. I know. So I should stop. Anyway, that's my introduction to lines for you guys, and we'll next class is the quiz and the review. Test class after that, the test, and then when we pick back up again, I'll have a worksheet where I'm asking you guys to do these. All right? So, thanks. Can you hit the stop record for me?